And y'all let me know if you can see my slides. Oh, it says it's loading. I don't know. There we go. So again, thank you everyone for joining. Happy Tuesday. Yeah. After the long weekend, it's crazy how time flies. My name is Ana Aranda. I am the community outreach coordinator for the NASA Scope team, and we are a science activation team within NASA's science activation community. So real quick, we are need to move y'all. We basically connect subject matter experts such as yourselves to outreach opportunities. And within that, we provide like training, funding opportunities, just ways to connect and network. So this is one of the projects that we are partnering with the Solar System Ambassadors on to bring heliophysics big year topics to you all so you can continue to share that within your own communities. So if y'all would like to know more about NASA Scope, I can put some of our links in the chat. But basically, if you like to do outreach, which I'm assuming you all are since you're part of the Solar System Ambassadors group, feel free to connect with us. We're always looking for more ways to connect with other teams across the U.S. And especially with the eclipse that just happened, there's going to be more events that are continuing throughout the year. So yeah, I'll put all of our information in the chat, but basically we connect you all to outreach opportunities. And yeah, if you have any questions, I'm going to put my info in the chat, as I mentioned. But we're just going to dive in because I know Cristian has a packed schedule for us, all great topics. So yeah, as I mentioned, our guest speaker today is Cristian Ferradas. He's on the line right now. So he is a research scientist in the Geospace Physics Laboratory at NASA Goddard in the Department of Physics at the Catholic University of America. He graduated from the Department of Physics at the Catholic University of Peru, which is super awesome, and received his PhD in space physics from the University of New Hampshire. His research focuses on magnetospheric physics, which he's going to talk more about. But yeah, so take it away, Cristian. I will stop sharing so you can start sharing your slides.
All right. Thank you very much, Anna. Yeah, thank you very much for the opportunity to speak to all of you. Hello, everyone. I am very happy to share a little bit of science tonight, and especially, the kind of science that I do. So I'm very excited to share with you some slides. So let me see if I can share. All right. Can someone confirm if you can see my slides?
Yeah, we can.
Awesome. See, okay. Perfect. All right. Well, thank you very much, Anna, for the kind introduction. Yeah, as Anna said, my name is Cristian Ferradas. I work at NASA Goddard Space Flight Center in Greenbelt, Maryland. I've been working here for 5 years now. Um, and I am part of the Geospace Physics Laboratory. And in this laboratory, we focus on, well, as the name says, in geospace, the near Earth space. Particularly, my research focuses on the magnetosphere. And therefore, I'm going to talk to you about the magnetosphere. So some of you might be familiar with the magnetosphere. Maybe some of you have never heard about the magnetosphere. So that's why this presentation is really an introduction to the magnetosphere. That's my goal, to introduce to you the magnetosphere and tell you a little bit about what the magnetosphere is, what it does for us. And actually, as you can see here in my title slide, I included this subtitle, Earth's protective bubble, to, right from the start, convey to you what the magnetosphere really is for us in the Earth. It's really something that protects us, is not a layer in the sense of the layers we find in the atmosphere. It's more like a bubble, and that's why I called it the protective bubble. And it fulfills a very, very important um, role in providing the conditions that we need on Earth to live and to thrive. So yeah, so today I want to talk to you about the magnetosphere, Earth's protective bubble, and I am going to dive in. And if you have any questions, feel free to raise your hands, or we can just save time. I will definitely save time at the end for questions. So I will keep my watch gear really close to be able to leave time at the end. But feel free to raise your hands or type any questions in the chat as well, and we can um, address them. Okay, so let me show you my outline for today. So a glimpse of the magnetosphere. So this is what I'm going to attempt to explain to you. The magnetosphere's origin, where it comes from, why do we have a magnetosphere, a little bit about the structure of the magnetosphere, what do we find in the magnetosphere, then sources, where does the stuff in the magnetosphere comes from, then I'm going to talk about a little bit about energization, which is a very important aspect of the magnetosphere. We find material particles that are highly energetic. So how does this energization occur? Then I'm going to talk about losses. At the same time, we have sources, stuff coming into the magnetosphere, and at the same time, we have losses, material leaving the magnetosphere. And then I'm going to finish with a little bit of the dynamics about the magnetosphere. Yeah, how do all of these other aspects of the magnetosphere come into play and really determine the dynamics of the magnetosphere? And at the end, I've saved some bonus slides about the space weather as well, the implications for space weather. So anyway, let's start. So first, let's start with the origin. Okay, so where does the magnetosphere come from? Why do we have a magnetosphere? So we have to start with our planet, of course. And as you know, our planet Earth is the third one in the solar system in order from the sun. And it has, among its several very unique characteristics, one characteristic that really makes our planet a giant magnet. Many of you probably already know this. We don't fully understand how this magnetic field of the Earth comes to be, but our best explanation is that we have molten iron in near the core of the Earth, and that creates a magnetic field, not only at the Earth's surface, but even beyond and much farther distances from the surface of the Earth. So here you can see just a very uh, simple diagram of the Earth. And in every figure that I'm going to show where the Earth is, I'm going to specify if this is a side view or a top view. You can see here at the bottom left, I will indicate, because I know this can be a little confusing, and sometimes we scientists are used to these diagrams, but sometimes I will show diagrams from the side view, and sometimes I will show some figures or plots from a top view. Like top view would be showing the equatorial plane where the Earth is at the center. But anyway, so in this side view of the Earth, you can see these white lines representing the magnetic field lines, leaving this southern hemisphere and going all the way to the opposite hemisphere. And it was actually first proposed many, many centuries ago by William Gilbert that the Earth was a magnet, and that's why we could use instruments as compasses. And one interesting characteristic about the magnetic field of the Earth is that the magnetic poles, as you can see here in this figure, are not necessarily aligned with the geographic poles. Actually, the magnetic axis, let's say, is tilted roughly 11 or so degrees with respect to the axis of our rotation. So anyway, this is the first characteristic to keep in mind. The Earth is a big magnet, and the Earth has a magnetic field. Secondly, we have to talk about the solar wind. The solar wind is this magnetized plasma that flows from the sun into interplanetary space. So a lot of people, when they think of outer space, they think that it's empty, but far from so. Actually, interplanetary space is filled with all these particles and radiation that the sun is blasting into space continuously. And this flow of plasma is what we call the solar wind. So this is another thing we have to keep in mind, that the Earth is embedded in a region of space that is filled with the solar wind. So let me show you a very interesting animation of how the magnetic field of the Earth interacting with the solar wind creates the magnetosphere. And in this simulation, we will start with the sun. So this black circle here is the sun, and the units being plotted here in the X and Y axis are radius of the sun. And you will see in this simulation how the sun ejects mass in the form as a coronal mass ejection, and you will see how this travels into interplanetary space until it reaches the Earth. So I'm going to play this for you. Hopefully you can see this. So there you can see this ejection of mass from the sun into interplanetary space. You can see how far we are from the sun, roughly here, right? Like 150 sun radii. And then we're going to zoom in into this particular region of space. And right there, lo and behold, that's us, tiny Earth in the middle of the flow of the solar wind, interacting with all this stuff that comes from the sun, called the solar wind. And in this animation, this is a computer simulation made by a group at University of Michigan. You can see these, again, white lines on the left side, and this represents the magnetic field of the sun. And then the same white lines inside this region around the Earth are also magnetic field lines, but from the Earth. So you can see that the magnetic field lines from the Earth are interacting with the magnetic field lines from the sun. And this interaction is very important. And so the magnetosphere really is the result of this interaction, right? The interaction between the Earth's magnetic field and the solar wind, which carries with this flow of plasma, of particles and radiation, also the sun's magnetic field, right? So we have sun's magnetic field interacting with the Earth's magnetic field. And it creates this bubble-like structure that we call the magnetosphere. And just to talk about a little bit about the shape of the magnetosphere, you can see from this diagram, which is also a side view with the sun to the left, you can imagine the Earth as a rock, right, that you would place in the middle of a river or some kind of flow. And so on the upstream edge of that rock, right, you create what we call here a shock. So the bubble, right, that we call the magnetosphere is compressed towards the sun, so looking towards the sun, and then away from the sun, like downstream, right, we have an elongated structure, and that's what we call the magnetotail. So we also refer to these two regions, towards the sun and away from the sun, as the day side, the region towards the sun, the region where the magnetosphere is compressed by the incoming solar wind, and we refer as night side to this magnetotail region where we have this elongated region away from the sun, right? So remember these two because I'm going to be referring to these day side and night side regions of the magnetosphere. Day side towards the sun, night side away from the sun. So, okay, let's talk about the structure of the magnetosphere. So the magnetosphere, our magnetic bubble, is not empty. It's filled with charged particles, and these charged particles are also called plasma. They form a plasma, natural plasma. And one key characteristic of this plasma is this characteristic that we refer to as the frozen-in condition. And what does this mean, this frozen-in condition? This means that the plasma is tied or frozen in to the magnetic field lines. So if the magnetic field lines move, the plasma particles move with the magnetic field. So the plasma obeys or responds to the magnetic field lines, and vice versa, right? If the particles move, then the magnetic field moves with the particles. So they are tied together or frozen in. So that's one characteristic to keep in mind. Now, let's talk a little bit more in detail about magnetospheric structure. So the magnetosphere is a quite complex region. It's very dynamic, as I'm going to try to explain a few slides later. And partly all this complexity and the dynamics of the magnetosphere is given because the magnetosphere is composed of diverse plasma populations. So here I'm going to introduce just a couple of regions or plasma populations in the magnetosphere. So for example, we have the bow shock and the magnetopause. So the bow shock is this boundary where outside of it we find the solar wind, and the magnetopause is another boundary that defines which is the outer boundary of the magnetosphere, actually. So the magnetopause is the outer limit of the magnetosphere. And in between the bow shock and the magnetopause, we have this region called the magnetosheath. So the magnetosheath has particles, has material from both. Particles that make it through the bow shock into the sheath from the solar wind, and some particles that come outward from the magnetosphere through the magnetopause into the sheath. So the sheath contains plasma from both origins, the solar wind and the magnetosphere. So then we also have a very important region in the magnetosphere that's called the plasma sheet. And remember, this diagram here is also a side view. So we have the sun to the left, the Earth is right here. We have the magnetic field lines, these black solid lines. So this plasma sheet is a region that's very close to the equatorial plane. So very close to the equatorial plane, we have this region, the plasma sheet, that acts as a reservoir of plasma. I'm going to talk about this plasma sheet a little bit more later, but just remember that the plasma sheet is the big reservoir of plasma in the magnetosphere that provides plasma to other regions of the magnetosphere. So then we have this region in the magnetosphere, which is the innermost region of the magnetosphere, that's called the inner magnetosphere. And this is my favorite part of the magnetosphere. And of course, I'm biased because this is the region that I particularly study. So the inner magnetosphere is the region where we find particles that get trapped in Earth's magnetic bottle. So why do we call this region as Earth's magnetic bottle? You can see that the magnetic field lines, all of them converge near the poles, right? Near the equatorial plane, they are not converging. They are just in flowing or just connecting the two poles. But near the poles is where all the field lines converge. So these two regions create what we call this magnetic bottle, which means that particles that get into this inner magnetosphere region can get trapped, and they bounce from one hemisphere to the other hemisphere along the field lines. And that's why we call them trapped, because they bounce back and forth between the northern and southern hemispheres along the field lines for a long time sometimes. So some of the particles that get trapped in this region are very energetic, and we're going to talk about that as well. But anyway, to start with, this inner magnetosphere region is where some trapped particle populations exist. And we're going to talk about this a little bit more because this is very interesting. So let's talk about the inner magnetosphere. This is a very dynamic region. As I mentioned, several plasma populations coexist in this region. So let's talk about the first one. The first one is the plasmasphere. And the plasmasphere is the region with the densest plasma and also the coldest plasma. So we have the energy of the particles in this region, in the plasmasphere, are roughly the energy of about 1 eV. And this is very cold. I'm going to show you a diagram later where you will get an idea of what the energy of these particles are compared to, for example, the air that we breathe here at the surface of the Earth. But for now, just remember that the plasmasphere is a very dense and cold population of plasma. Next, we have the ring current. The ring current is composed of particles that are more energetic than the plasmasphere. Their energies are roughly between 1 and 500 keV. So you can tell that these particles are roughly 1,000 or 100,000 times hotter or more energetic than the plasmasphere. So much, much, much more energetic plasma. And remember the ring current because we're going to talk more about the ring current as well. Next, we have the radiation belts. And maybe some of you have heard about the radiation belts because probably the radiation belts or the Van Allen belts are the most popular of these three plasma populations in the inner magnetosphere. And for a reason, which is that these population are the most energetic population. It contains particles that are relativistic. That means that their energies refers or converts to velocities that approach the speed of light. So when we talk about the radiation belts, we're talking about energies of 1 MeV or above, right? So this is 1 million times hotter, at least, than the plasmasphere. So this is the third population in the inner magnetosphere. And as you can tell from this cartoon here, we have two radiation belts. We have the inner belt, and then we have the outer belt. So we have two radiation belts. That's why we refer to them as the belts in plural. So one is closer to the Earth, and one is farther from the Earth. And both of them, especially the outer belt, is very dynamic, and there's a lot of study going on radiation belt physics. So the interesting thing about these three plasma populations is that they overlap in space. So even though they are distinct, they are not spatially separated. So they coexist in space. So the way we distinguish them is actually by their energy, by their temperature, by their density. By these characteristics is how we identify these different plasma populations. But spatially, they coexist, as you can see in this cartoon. And this is why the inner magnetosphere is so complex, is so dynamic, because all of these populations are coupled. They interact with one another via different processes, like, for example, plasma waves. Waves are generated in this region, and the waves act as mediators between the populations, transferring energy from one population to the other, or transferring or transporting particles as well from one population to the other. But so remember that the inner magnetosphere, then, it's a very dynamic and complex region because of these populations that interact and coexist in space. So yeah, this is the chart that I was referring to earlier. So here, I just want to give you an idea of the magnetospheric parameters. So here in the x-axis, you can see the density of the populations that I just talked about. And here in the y-axis, you can see the temperature or the energy. And as a reference, here you can see the temperature and the density of the neutral gas at Earth's surface. So you can see that at Earth's surface, the air we're breathing in our atmosphere can be very, very dense and very, very cold, at least relatively speaking. So compared to the neutral gas at the surface of the Earth, the plasmasphere, right, the cold, the dense population is way less dense, first of all, but quite hotter, right, quite more energetic than the neutral gas at the surface of the Earth. maybe roughly 2 orders of magnitude hotter. Then when we talk about the plasma sheet, it's even less dense, but significantly more energetic. And then when we go to the ring current, we continue this trend. With increasing energy, the ring current is less dense, but quite more energetic. And finally, the radiation belt is the least dense population, but its energy is roughly 8 orders of magnitude hotter than the particles at the surface of the Earth. And we're going to talk about more about the energization of these particles later. But for now, I just wanted to give you an idea of these just 2 parameters, density and temperature, of the plasma populations in the magnetosphere compared to the gases at the surface of the Earth. Okay, now let's talk about the sources of the magnetosphere. Basically, we have 2 sources of the particles in the magnetosphere. And the first one is the solar wind, right? So as I mentioned at the beginning, the Earth and the Earth's magnetosphere is embedded in this flow called the solar wind. Now, for a large part and to a large extent, the magnetosphere shields us from all the solar wind that is flowing continuously. But some solar wind particles make it inside the magnetosphere. There is one particular process called magnetic reconnection that I mentioned here that is responsible for allowing solar wind particles to enter the magnetosphere. So given some particular conditions, magnetic reconnection can happen either here on the day side of the magnetosphere or also in the night side here of the magnetosphere. And when that happens, solar wind particles can enter the magnetosphere following a similar path as I'm showing here. So then we have, when we're inside the magnetosphere, we have particles coming from the night side towards the day side, along the tail, towards the Earth. The second source of plasma or particles or material in the magnetosphere is actually the ionosphere, which is the conducting layer of our atmosphere. And the ionospheric source is particularly important during periods of strong activity. For example, during geomagnetic storms, we have a lot of particles from the atmosphere, from the ionosphere, flowing along the field lines into the magnetosphere. And this has been observed abundantly via satellite missions, for example. And there are 3 particular regions where particles from the ionosphere flow or outflow, as we call it, into the magnetosphere. One region is the auroral oval. So this region is where auroras are observed at these particular latitudes. The same way we have some particles coming in from the magnetosphere down to the atmosphere, we also have particles flowing the other direction, and we call that outflow. And that those ion beams or ion conics or ion outflow is one way, or the auroral oval is one region where this ion outflow can take place. But we also have another region called near the polar cap here, and that is called the polar wind. So the polar wind is another region where ions and particles flow from the ionosphere to the magnetosphere. And the third one is the cusp. And the cusp is actually a region that is open to the solar wind. So this is another region where particles from the solar wind can stream down all the way to the atmosphere. And likewise, we can have particles flowing in the opposite direction. So in these 3 regions, the cusp, the polar wind, and the auroral oval, in these 3 regions, we can find ion outflow from the ionosphere into the magnetosphere. So then we have these 2 sources, the solar wind and the ionosphere, one from outside, one from inside. So the magnetosphere has particles from both, from the inside, from the outside. Okay, so now let's talk about energization. So this is a big mystery, actually, right? Let's look again at this plot that I showed previously. And right away, right, an immediate question that is raised by this graph is how do particles, right, from the two sources, right? The solar wind and the ionosphere with the respective energies plotted here, the solar wind with energies of roughly 1 keV, and the material from the ionosphere with energies roughly of 1 eV or below, as illustrated here. How do these particles get energized to the energies that we observe in the magnetosphere? For example, radiation belts and the plasma sheet, several orders of magnitude more energetic than the sources, right? So this is one of the main mysteries in the magnetosphere. This has been studied um, continuously for decades, and we have some ideas, but this question to a large extent is still open. We're still observing, we're still finding very, very energetic particles in different regions of the magnetosphere, actually, sometimes where we don't expect to find them. And immediately this question is raised again. How do particles get energized to such high energies? So some energization mechanisms, not all of them, are the ones listed here. Adiabatic heating, for example, is a main one, illustrated in this diagram here. Again, this is the Earth. We have the magnetic field lines going from one hemisphere all the way to the other hemisphere. And adiabatic heating refers to one property of the plasma in the magnetosphere that tells us that some quantities must be conserved in the magnetosphere. As particles move from one place to another, some particles must be conserved. And we call these quantities adiabatic invariants. So basically, this formula just tells us that if a particle moves from a region farther from the Earth to a region closer to the Earth, immediately, so that this adiabatic constant can be constant, can remain constant, the energy must increase. Because the magnetic field gets stronger as we move inside, right? So if we go from a region of weaker magnetic field to a region of stronger magnetic field, then as a consequence of that, and to preserve the adiabatic constant, then the energy must increase. Similarly, we have Fermi acceleration. Fermi acceleration is similar to adiabatic heating, but refers to the motion parallel to the magnetic field lines, right? When we talked about the adiabatic heating, we're talking about motion perpendicular to the magnetic field lines. But Fermi acceleration refers to particles that are bouncing, as I mentioned before, trapped in this magnetic bottle from one hemisphere to the other. And as these particles bounce from one to another hemisphere, and they move because they're frozen in, right, to the magnetic field lines, as the configuration and the location of the magnetic field lines changes, then the energy of the particles also changes. The third one is wave-particle interactions. I briefly mentioned before that one consequence of these overlapping populations and the interaction of the populations in the inner magnetosphere is the generation of waves. And the waves fulfill or play a very, very important role in the magnetosphere because they can cause energization of the particles. They can cause precipitation, that is like change in the trajectory of the particles. So the waves are very important, and waves can also energize particles when they interact resonantly with them. And finally, we have impulsive electric fields induced by changes in the magnetic field. So whenever we have a magnetic field that's changing, that change in the magnetic field induces an electric field. And this induced electric field can energize particles. And this can be very important again, especially in periods when the magnetic field lines or the magnetic field is changing rapidly, like, for example, during substorms or storms, where the magnetic field of the Earth is being compressed in a stronger way, can be enlarged towards the tail. So during any period when the magnetic field is changing rapidly, electric fields are induced, and these can energize particles. So these are just some very few, but some of the main energization mechanisms. Okay, let's talk about losses. We already talked about sources, how particles and where particles come from, and how they get to the magnetosphere. So now let's talk about the losses. Particles can also be lost from the magnetosphere. Now, in this diagram, we have the Earth here at the center, and this is a top view of the magnetosphere. So we have, again, the sun to the left. Here we have the magnetopause, and this is the equatorial plane in the magnetosphere. So what happens to all of the material in the magnetosphere? A first loss mechanism is magnetopause loss. And that refers to the fact that we see, as I mentioned before, we have this flow of particles from further down the tail towards the day side, so from the night side to the day side. And as these particles flow, following paths that are similar to these lines, these solid black lines, they go all the way to the day side and they hit the magnetopause and they get lost. So particles can flow also from inside the magnetosphere out through the magnetopause into the solar wind. Another loss mechanism is charge exchange with the neutral atmosphere. So as these particles are flowing from the night side to the day side, they interact with the atmosphere. And actually the outer layer of the atmosphere is called the exosphere. And in this region, predominantly hydrogen atoms can interact with the hot energetic particles from the magnetosphere, right? So if we look here on the left, we have the incoming particles to the charge exchange reaction, which is the magnetospheric energetic particle. And we have the cold neutral atom from the atmosphere just sitting there in the atmosphere. So, but when these two collide, they exchange charge. That is, the ion steals an electron from the neutral. So the hot ion becomes a hot neutral. So it's not a charged particle anymore. And the cold neutral becomes a cold ion. So why do we call this a loss? Because the hot plasma particle is not a charged particle anymore. So this is one very, very important interaction that creates loss to the plasma in the magnetosphere, charge exchange. And a second one is particle, or a next one, a third one is particle precipitation to the atmosphere. And in this diagram, again, looking from the side, we have the magnetic field lines of the Earth. And as particles, again, are flowing through the magnetosphere and are moving along the magnetic field lines, as I mentioned, right? Because some of them can be trapped. Some others are not trapped, but still they are bouncing back and forth along the magnetic field lines. So some of these particles get too low. When they get too low, they can collide with atmospheric particles and they become lost. And actually, this is what we call particle precipitation, because particles from the magnetosphere precipitate into the atmosphere. And once they collide with particles in the atmosphere, they interact with the atmosphere and they produce a variety of phenomena. And some of the most known phenomena, of course, are the beautiful displays of lights that we see near the northern and southern poles, which we call the aurora, right? So the aurora are caused by these precipitating particles from the magnetosphere into the atmosphere, interacting with the particles, exciting them, and then these atoms and molecules in the atmosphere, when they de-excite, they emit this light. And this light can take different colors, as you can see. Sometimes we have green aurora, sometimes we have red aurora, and the color depends on the particles in the atmosphere that get excited and de-excited. So particle precipitation is a very, very important loss mechanism in the magnetosphere. Of course, from the ground here, we see the beautiful display of the aurora, but if we look at it from the magnetospheric side, it's a loss mechanism because we're losing particles outside of the magnetosphere. Okay, let me finish up with the dynamics. We still have a couple more minutes, so I want to quickly talk about the dynamics of the magnetosphere. So how do all these aspects of the magnetosphere we have described so far, the origin, structure, sources, energization, losses, how do they combine to determine its dynamics and activity, and especially during geomagnetic storms? So there are different, let's call them cycles or events or phenomena that display the activity in the magnetosphere. But probably the most known and the most important, arguably, is a geomagnetic storm. So that's the one I want to focus here and talk about a little bit. So what is a geomagnetic storm? Maybe some of you have already heard about geomagnetic storms. For example, earlier this year, we had a huge geomagnetic storm, right? You probably heard the strongest in at least 20 years. Okay, so what is a geomagnetic storm? Well, according to Wikipedia, right, our go-to source for information, a geomagnetic storm is a temporary disturbance of the Earth's magnetosphere caused by a solar wind shockwave. Okay, so hopefully after my previous slides, you can recognize some words here, right? The Earth, the magnetosphere, solar wind. We haven't talked about the shockwave, but you can imagine, right? You can recall my simulation and one of my first slides where you saw this coronal mass ejection flowing through space, and when it hits the Earth, that's a shock wave. But okay, let's go a little deeper and let's look at this paper, one of my favorite papers, by Walter Gonzalez. And you can tell that this paper focuses on geomagnetic storms. Actually, the title of the paper is "What is a geomagnetic storm?" So in this paper, we get a very interesting definition. So I'm going to read it for you. A geomagnetic storm is an interval of time when a sufficiently intense and long-lasting interplanetary convection electric field leads through a substantial energization in the magnetosphere ionosphere system to an intensified ring currents sufficiently strong to exceed some key threshold of the quantifying storm time DST index. Okay, that's much longer than the Wikipedia version, right? But I'm hoping that at least you can pick up one term here, intensified ring currents. So this is key when we talk about a geomagnetic storm. So a geomagnetic storm is tightly and very closely connected to an intensified ring current. And hopefully you remember that I already mentioned the ring current, right? It's one of the energetic populations in the inner magnetosphere. Okay, so if an intensified ring current produces or leads to a geomagnetic storm, before talking about that, I just want to very quickly show you what this DST index looks like, right? Because here in this definition, it pretty much says that a geomagnetic storm is an event where the DST index exceeds a threshold in the a threshold, a given value. So here you can see this is a plot of May 2024. And actually, this is time in the x-axis. And here is the whole month of May plotted. So you can see here, actually the storm of May 10, 11, 12 of this year. And you can see the DST index has a value of 0 at here. And so the geomagnetic storm is characterized by this very sharp decrease in the DST index. Roughly speaking, if this index goes below a threshold of -50, we call it a storm. And for the last 20 years, we pretty much didn't have any storms that went below -200. But this May 2024 storm reached a peak of exceeded -400 nanotesla in DST. And that's why we are all very excited with this storm. And we're already studying this storm in much detail. But anyway, so this is how we quantify a storm by this index. And this index pretty much just measures how much the magnetic field at the surface of the Earth is disturbed. So when it's significantly disturbed, then we call it a storm. Okay, but going back to our definition, we have an intensified ring current at the heart of a geomagnetic storm. So what is the ring current, or how is the ring current intensified? So for this, we have to remember about the plasma sheet, right? We already mentioned the plasma sheet, this region in the tail of the magnetosphere that acts as a reservoir of plasma. So this reservoir of plasma, particles that come from this plasma sheet region, they undergo a variety of processes that we have already mentioned, right? First, we have that some of these particles, they flow towards the day side and they exit the magnetosphere through the magnetopause, right? And this is a loss mechanism. We also have that some of these particles will exchange charge with the cold atmospheric atoms, right, via charge exchange. And this is another loss mechanism. Then some of these particles will precipitate to the atmosphere, right, causing the beautiful aurora, which is another loss mechanism. But some of these particles, as they flow, again, from the night side to the day side, will be energized and will be trapped in the magnetic bottle and will form the ring current. So this is an energization mechanism. And some particles will also be trapped and further energized to form the radiation belts, which are even more energetic. So can we observe the ring current enhancement from space? Well, yes. And I'm just going to mention one particular space mission called the Van Allen probes, which again, here just to refresh your minds, this is the ring current in a very basic cartoon, of course, roughly where the ring current is. And this is one orbit of the Van Allen probes, which is surveying exactly the region of interest through the ring current. And this is what the measurements look like. This x-axis is the time. Here is the DST index, or the high resolution version called the SIM-H index. And you can see here right in the middle of the plot, we have a storm. And here the three panels, they represent the y-axis is energy, and the color is pretty much the intensity of the particles. So redder means more particles, bluer means less particles for different energies. And the three different panels are just three different ion species in the magnetosphere. So without going into the details, you can see, first of all, that this tiny interval here is one full orbit of the Van Allen probes. So throughout this storm, throughout the whole period plotted here, we have multiple orbits of the Van Allen probes. And you can see that when the storm starts, the ring current gets intensified significantly. You can see how the color changes during the storm. So yes, we can observe the ring current enhancement from space. Next question, can we simulate the ring current enhancement with computer models? Right, you probably have heard, or maybe you're wondering if we can simulate this to better understand the ring current and geomagnetic storms. Well, the answer is yes. And again, I'm just going to show one example of a model, which is the Comprehensive Inner Magnetosphere Ionosphere, or CIMI model, which is a model developed at NASA, at Goddard, actually by my group, so I'm biased. Talking about this model is the model that I work with here at NASA, but it's a model that focuses in the inner magnetosphere and in the ionosphere, particularly on the ring currents. So using this model, we can simulate the ring current, right? If you remember my previous slide showing the Van Allen probes observations, let me quickly go back there. The Van Allen probes can only give us measurements along its orbit, right? So only along this path, but we don't know what's happening at, all around and other regions in the ring current. That's why simulations are very important, because now in these simulations, again, with a top view, we can simulate and get an idea of what the ring current distribution is in the whole equatorial plane, right? So we get a much, much fuller picture of the dynamics of the ring current. So here in this top panel, again, you can see the DST index. If you look at the blue curve, that's the measured index. And this is the period when it's decreasing. So this is the storm. And these four magenta lines are these periods corresponding to the plots being plotted here. And you can see at those particular times how the ring current is evolving throughout the storm, right? Particularly here at time 2, near the peak of the storm, you can see how significantly enhanced the ring current is compared to before. And actually, the red curve here is the simulated DST index. So because the ring current is so closely connected to a geomagnetic storm and to a DST index, there are formulas that can convert the ring current energy into a DST index. So using our simulation, we can calculate a simulated DST from our model. And you can see that the simulated DST in red follows pretty well the measured one in blue. Okay, well, that's all I have regarding the magnetosphere, regarding the dynamics of the magnetosphere. We are approaching the end of the hour here, but I quickly want to talk about space weather. Hopefully, you guys can stay a little bit for questions. I will only take a couple more minutes of our time, but I briefly want to talk about space weather because space weather is something that is very relevant to us. Probably you have heard about this, and it's something that's tightly connected with the magnetosphere as well. So again, I like starting with definitions. So what is space weather? This is a definition that I found in this paper by Eastwood, 2008. And the definition goes, the term space weather is defined as the conditions on the sun and in the solar wind, Earth's magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-based technological systems and endanger human life or health. So space weather is very important for us. So because of that, of course, NASA and the government, of course, through NASA has invested a lot of effort in creating a fleet or an observatory, as we like to call it, NASA's Heliophysics System Observatory, composed of an army of space missions that are illustrated here in this plot that are orbiting different regions of the magnetosphere and also in the solar wind, some of them further down in the upper atmosphere, monitoring and taking measurements of the near-Earth space. And all of them, or at least some of them, have direct space weather applications. So what are some of these space weather effects? So large fluctuations in the magnetic field of the Earth, like for example during geomagnetic storms, can induce electric fields, like I explained earlier, and can also induce electric currents flowing through the magnetosphere. And these currents can travel all the way to the ground and close at the surface of the Earth, and they can cause severe damage to energy distribution networks and corrode underground pipelines. All of these damages have been recorded, so you can very quickly do a Google search and find specific examples of all of these effects. Another effect is during periods of intense solar activity, radio communications can be disrupted. Right? This forces sometimes airplanes to deroute from their near polar trajectories to other alternative routes because of the dangers involved with being exposed to extreme solar energetic particles, for example. So even air flight is affected by space weather. And as we go up, we have other technologies that we have in space also being vulnerable to the effects of space weather. For example, radiation and energetic particles from the solar wind can induce satellite anomalies. For example, surface charging. For example, dielectric charging. Dielectric charging is just when particles are very, very energetic particles penetrate the shielding of the spacecraft in space from the satellites, and they deposit energy and charge into instruments, into any type of machines, electronics, and they can cause severe damage to all of these. They also create anomalies in solar panels, like degradation, and they create spurious counts in sensors, contaminating the measurements. So this is something that we have to deal with, all of us that deal with data. So these are other effects of space weather. And finally, of course, as we continue to go up, we find astronauts in outer space, and solar eruptions can also represent a hazard for our astronauts when they are, especially when they are outside the shuttle. Okay, so that's all I have. Thank you very much. Here I listed some sites for further resources. Suntrack is a very cool website with full of resources geared towards education as well. So all of you that like sharing science with other people, I think Suntrack will be a great resource for you. And yeah, I've also uploaded my slides from this talk into my website right here. But I will stop here and take any questions.
I have a question
Hey,
about
Christian.
the DST versus the KP factor that we're more commonly used to seeing with the NOAA sites. How does those two relate?
Yeah, good question. Very good question. So the DST index is an index that it's a very good measure, as I showed in my slide. It's a very good measure of the intensity of the ring current. The KP index is a more global index in the sense that it doesn't only measure the intensity of the ring current, but it measures other phenomena as well. There have been studies particularly showing that the KP index is very well correlated with something that we call magnetospheric convection, which is pretty much the level of the electric field of the solar wind entering into the magnetosphere. So the electric field flow creates an electric field. Sorry, the solar wind flow creates an electric field, and this electric field penetrates the magnetosphere. And when it inside the magnetosphere, we call it the convection electric field. So the Kp is a very good measure of this convection electric field. So the Kp index has been used to, for example, to predict aurora visibility. Again, because many phenomena are related with this convection phenomenon. So yeah, I think that's probably the main difference between DST and KP.
There's not a like a numerical relationship between the two.
No, that I know of. No, these are
Okay.
measurements and they are not necessarily correlated. No.
Okay, thanks.
Yeah, thank you for the question.
Hey, Christian, there's a lot of um, questions in the chat.
Okay.
Um, do you want me to read them off or?
Okay, I can take a look. Okay. Do you have comparative magnetosphere research with other planets in our solar system or elsewhere? Well, I don't personally do. It's something I would like to do. Maybe in the future I will do, but there's a lot of people doing comparative magnetosphere research, comparing our magnetosphere with, yeah, those of all the other planets that have, but I don't personally do comparative magnetosphere research. Another question. Have we developed any theories to explain the possible cause mechanism of Earth's magnetic field reversals? Very good question. Um, Not that I know of. Uh, yeah, paleomagnetism is a total different field. In magnetosphere research, we don't deal too much with these very long-term changes like magnetic field reversals on Earth. Of course, these occur way at shorter timescales in the sun. We have the 11-year solar cycle, which is the reversal in the case of the sun. In the case of the Earth, we know that this is way slower, to the point that we don't really need to worry about it for at least for our daily lives, and for space weather effects and for magnetospheric research to a large extent. So I am not really aware of this, to be honest. So I am not the best person to answer this question. Sorry. Another question from Dennis is the distance between the North Magnetic Pole and the geographic North Pole called variation isogonic lines. I am actually not sure. I don't know the name of the distance between these two poles. But I do know that this distance is changing, of course, because the poles are drifting with time. What do the colors represent in the animation? Okay, this probably is the first simulation that I showed. Yes, good question because it was not explicitly said. I think it's density. I can remember for sure. But my best guess would be that it's density of the particles. Is this the same type of plasma that's considered a fourth state of matter? Yes, that's correct. Yes. So yeah, unfortunately, we don't have many examples of natural plasma like here near the surface of the Earth. That's why we usually just think of and say we have three states of matter. But yes, we usually say that plasma is the fourth state of matter. And actually, funny fact, 99, at least 99% of the matter in the universe is in this fourth state of plasma, in the plasma state. And this, of course, has to do with the fact that stars are plasma, and stars are way, way more massive than anything else, pretty much.
There's a really cool website that really talks about that goes back decades ago that they realized that most of the universe was in this state.
Yeah, thank you. Okay, Francisco says, how much of our magnetospheric shields or magnetosphere shields the moon? Good question. Yeah, the moon sometimes is within the magnetosphere, but sometimes it isn't. It's in the solar wind. Tushar says the different spheres intersect one another. Oh, got my question answered. Okay. Another question. And how are these zones related to the auroras? Oh, this probably refers to some slide, but I'm not sure which one. Okay, follow-up question from Tushar. When they interact with each other, probably the inner magnetospheric populations, do they alter their shapes? Yes, they do. Yeah, the shapes of these populations in the inner magnetosphere, they change significantly. And from my slide showing the simulation of the ring current, you can get an idea of how at least the ring current is changing in shape significantly throughout the storm, not just in intensity. Um, Doug says, recently an electrical and bipolar field has been discovered surrounding Earth. Do you know where this field exists around our Earth? Yes, so this ambipolar electric field is actually has been very mysterious, but it's understood to be very important, especially in allowing particles to outflow into the magnetosphere. So particles leave from the atmosphere into the magnetosphere, as I explained at some point. Remember when I talked about the sources, the ionospheric source, this outflow needs require some energization for the particles to be able to overcome the gravitational pull and be freed into to go into the magnetosphere. So this ambipolar field is believed to exist in that region in the upper atmosphere. Let's call it the transition region between the atmosphere and the magnetosphere, where this ambipolar field is understood to play this very, very important role. What happens at the X points of the Earth's magnetic field? I'm not sure what the X points are, unfortunately. What happens when the sun's magnetic poles flip? So they flip every 11 years, and this creates the solar cycle. And I guess the main consequence of this solar cycle is that we have periods of that we call um, maximum of the solar activity, and then we have periods of minimum of solar activity. So we refer to them as solar max and solar min. So during periods of solar maximum, the sun is more active, as the name suggests, and we have many more explosions, many more all sorts of phenomena occurring in the sun. And of course, the likelihood of those reaching the Earth is also higher because we have more events. Actually, right now we are in or approaching solar max, and that's why we have had several very interesting events recently, including the storm of May of this year. Adrian says, is the Earth's climate more susceptible to the effects of the solar wind, charged particles, as the climate is changing? The Earth's climate more susceptible to the effects of the solar wind, charged particles, as the climate is changing? I don't think so. At least to the best of my knowledge, there's no real correlation between um, the climate changing and the particles and the solar wind. particles. Don't quote me on that. Um, but this is not my field of expertise. I'm sure there are people trying to make these connections, but I really don't know what the results of these are. I'm hoping to get to Iceland in March to see the Northern Lights. Can you figure out what colors will be most prominent during the time? Probably not, because the colors have to do with the atoms and molecules, the particles in the atmosphere. So it will depend on the energies of the particles coming in, how deep in the atmosphere they can go, and therefore what atoms and molecules they can excite. But of course, this is very difficult to to forecast or to predict.
Can I ask you a question sort of related to the frequency of auroras? We were just in Alaska for the last 3 weeks, and we saw the most beautiful aurora that went on almost 2 hours long, and near Ketchikan, Alaska. And what I was sort of surprised about is sort of in that aurora oval that you talked about, they must be very frequent, right? Even just the normal solar wind is causing them almost most of the time, right?
You mean the aurora must be very frequent?
Yeah, I guess in those northern latitudes, just from the normal solar wind, they're seeing them. I mean, I heard that his number as high as 200 days a year out of the year.
Yeah, I would
Even
think
even
so.
even not during a storm, that they're basically seeing it within that oval. You can see it pretty
Hmm.
strongly most of the time, right? I was
Yeah.
just amazed. I was amazed at that northern latitude of Alaska, that where we saw it, that this wasn't a transient thing. It was very dynamic, and it went on for 2 hours. And
Hmm.
it was just I've seen aurora before in northern Michigan, for example, but I'd never seen anything like that just went on and just pulsated. And it was, sometimes it was bright that you didn't need a camera to see the reds and the greens. It was just amazing. But they were telling
Yeah.
me that they can see as many as 200 nights a year. They can see aurora, not quite that extreme. I guess we got up to about a KP of 8 that night, or I'm sorry, 7.5 or 8, I guess.
Hmm.
But
Hmm.
but I was just amazed at the
Yeah.
intensity of it. Yeah.
Yeah. Yeah. Yeah. We
But
have
you
to
don't really need
remember.
you don't really need to go to Iceland. Just take a trip to Alaska, and you see it almost all the time, I guess.
Hmm. Yeah. Yeah. Well, you're a lucky one, having been able to see the aurora several times. But
Yeah,
yeah,
I guess I guess the only thing going against it is the amount of darkness in Alaska. Most of the summer is too long, but it's amazing. I mean, when you actually
hmm.
see one that's that intense, it's just kind of life changing.
Yes. Yes, for sure. For sure. Um, okay. Yeah. So Anne's question about the auroras and different colors, I think we answered that one already. Yes, it has to do with the different atoms and molecules, yeah, the particles in the atmosphere that are excited. Adrian says, if I remember correctly, Explorer 1 studied the Van Allen belts. So was that mission the start of modern heliophysics research? It was one of the first ones, for sure, Explorer. I'm not sure if it was the first one, but it was for sure one of the first ones. Yeah, it made very, very important discoveries, Explorer 1. Um, Gregory says, how can you be sure that the computer simulations are showing us reality? You may be programming the computer to show what you think is happening. Computer simulations rarely show the opposite of what was programmed. Yeah, very good question. This question has to do with how do we validate our models? But for that, I mean, the most obvious answer is we compare our measurements. Sorry, we compare our simulations with measurements, with observations, and that's actually one of the main tasks that I have in my job. I validate the models. For example, the model that I showed the results of in one of my slides. So we use measurements from that army of satellites that I showed in one of my slides from the Heliophysics System Observatory. And that's why all of those measurements are so valuable because, among other things, we can use those measurements to compare uh, against our models. And, that will give us very important information about how the models are doing. A lot of the times the models are doing very bad, and that, pushes us to know, okay, to understand why, why are they not working? Sometimes they work well in some periods, but some other periods they don't work well. So, we constantly are trying to ask this question of, how can we improve our models? And yeah, that's an ongoing effort all the time. But this is a very good question, and the answer is validation, right? We have to validate our models, and we do that all the time using measurements.
Part of
Uh,
the International Space Station at that altitude, I know they have a plasma measurement device on there. Is there any part of the magnetosphere or the ionosphere that would be measuring when they take those plasma measurements at that altitude?
at which altitude, sorry?
At the altitude that the International Space Station is orbiting at, just outside our atmosphere. Is that too far, too low in
No,
orbit?
no, no, no. That's low Earth orbit, and actually, we have instruments at the ISS taking measurements for space weather
Yeah,
as well
I
in our
I,
group.
volunteer, I volunteer at Wallop, and I know on the last
Hmm.
resupply mission they put another plasma measurement device up there, and I was just curious, how much is that contributing to your research?
Yeah, well, I haven't used measurements from the ISS too much, but we have used them. Yeah, actually, we have had this summer students, summer interns working with us, analyzing measurements from the ISS. This is our second or third year analyzing data from those, so it's very, very helpful.
So what part of the magnetosphere would that be measuring?
That's actually not the magnetosphere anymore. That's this transition region that I was mentioning. It's probably the ionosphere already. We're talking
Okay,
about maybe 400-kilometer altitude.
okay,
So that's the ionosphere.
okay.
So, for example, we have instruments measuring particle precipitation, right? That's the data, for example, that we have used in our group. So we can measure the particles precipitating from the magnetosphere into the ionosphere that cause the aurora. So that's one measurement that we have, particle precipitation.
How much farther out in orbit would you have to be to measure the magnetosphere?
Uh yeah, much farther. For example, the Van Allen probes, it um I don't want to give a number, but roughly, because when we talk about the magnetosphere, we usually talk about we use units of Earth radii.
Uh-huh.
So, Van Allen probes apogee. So the furthest point is, 6 Earth radii, and it measures all the way to maybe 1.1 or 2 Earth radii. So yeah, significantly higher.
Okay, thanks. That's helpful.
Hmm.
Hey, Christian.
Yes.
I think we might be at time. So I'm
Okay.
gonna take note of everybody's questions who hasn't been answered, and then I'll send them to you, and then we can send like a follow-up email later on.
Yeah,
But
that sounds great.
thank you so much for your time. Thank you everybody who joined. We have another presentation next week, next Tuesday at 3 p.m. So if you all are available, please show up for that one. That one's also going to be around auroras. So yeah, please sign up for that one if you haven't already. And thank you again, Christian, so much for your time. Thank you, Kay, for organizing this. And we look forward to seeing you all next week.
Awesome. Thank you so much.
Thank you, Christian. That was great.
Yeah, thank you for the questions.
Thank you. Yes, thank you very much, Christian. This was amazing.